Microphone looks like everything's working. All right. So today we should be able to get through 5.3 and 5.4. So far we're on track to be completely finished with lectures by either Thursday or Monday at the latest. So I'm hoping that gives you a couple of days to kind of rest and then go over everything and prepare for the final. So at least that's the plan, to give you a little bit of time in between the very end of class and the final to prepare to the best of your ability. All right, so let's finish up 4.3, the fundamental theorem of calculus. So let's say if we wanted to evaluate the integral from -4 to -2 of 3x to the fourth power plus 2x to the third power plus 4x plus 2 with respect to x. Okay, so the first thing I'm going to do, well, I'll just go ahead and rewrite it so I won't write on the original one. So from -4 to -2, 3x to the fourth plus 2x to the third plus x, plus 4x. Plus 2 with respect to x. Okay, so now we're just going to integrate each term. Okay, so we go ahead and factor out that 3. And the integral of x to the fourth power is x to the fourth power plus 1, well, 4 plus 1 power, divided by 4 plus 1. Plus 2 times the integral of x to the third power, which is x to the 3 plus 1 power divided by 3 plus 1. Plus, go ahead and factor out that 4. The integral of x, or just x to the first power, is x to the first power plus 1 divided by 1 plus 1. Plus the integral of 2 is just 2x. And you don't really have to put the brackets there, but I did it anyway. Okay, and that will integrate from -4 to -2. Or if you want, you can put x equals -4 and x equals -2, same thing. So whichever one works for you. You'll see the notation both ways. So okay. So the denominator 4 plus 1 will give us 3 over 5 times x to the fifth power plus we get 2 divided by 4, which is just 1/2 times x to the fourth power plus, if we go ahead and combine these two, we'll get 4 divided by 2, which is 2. So that's 2x squared plus 2x. And that's from x equals -4 to -2. So once you have it integrated, now you just apply, kind of separate that, the fundamental theorem of calculus. So first thing we do is we plug in our upper bound. So we're going to plug in that -2. And move this over as far as I can to try and squeeze it all in here. Okay, so that gives us 3/5 times -2 to the 5th power plus 1/2 times -2 to the 4th power plus 2 times -2 squared plus 2 times -2 minus, now we plug in the lower limit. We have 3/5 times -4 to the 5th power plus 1/2 times -4 to the 4th power plus 2 times -4 squared. So it's going to be a photo finish. Plus 2 times -4. Just enough space. And bring that down just a little bit so it doesn't look so cramped up in there. There we go. Okay, so we have -2 to the 5th power, which is 32 times 3, or -32 times 3. That gives us -96/5. Plus, we have -2 to the 4th power. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So that's +16 divided by 2, which is 8. Plus -2 squared is +4 times 2 is 8. And 2 times -2 is -4. And I'll go ahead because that's the first group of terms. Minus, we have -4 to the 5th power times 3 gives us -3072 divided by 5. Plus -4 to the 4th power divided by 2 is +128. Plus -4 squared times 2 is 32. And 2 times -4 is -8. Okay, so if we distribute this negative to all the terms there, that will give us -96/5. And we can add these two together. So you have 16 minus 4 is 12. So plus 12 plus 3072 divided by 5 minus 128. I could combine those, but minus 32 plus 8. Okay, so if you get these first 4 terms, which gave us these two after we combine the whole numbers, that would give you -36/5 after multiplying the 12 by 5/5, which would give you 60/5. Okay. Plus, we combine our whole numbers and multiply it by 5/5, that would give us -2312 divided by 5. which gives us 2,276 divided by 5. And again, normally they want it as, let me adjust that so you can see the whole page. There we go. They want the answer as a fraction, but they'll tell you if they want it as a decimal approximation or not. Usually they will. All right, so any questions on that one? All right, leave it up for a little bit. Bring it down. Here we go. All right. So let's say if we wanted to evaluate the integral from pi over 3 to pi over 2 of 3 times cosecant of x, and that times, let me put a bracket here, just so we won't have a bunch of parentheses flying around, times cotangent of x plus cosecant of x with respect to x. Okay, so for this one, we're going to have to remember that the integral of cotangent times cosecant with respect to x is equal to negative cosecant of x plus c. And again, with the definite integrals, we don't really need the plus c because they would cancel each other out. And we're going to have to remember that the integral of cosecant squared of x with respect to x is equal to negative cotangent of x plus c. Okay, so let me go ahead and just rewrite that. So the integral from pi over 3 to pi over 2 of 3 times cosecant of x. Oops, I have to put another bracket for some odd reason. Times cotangent of x plus cosecant of x with respect to x. So this one, probably the best approach would be to distribute that cosecant of x. And that 3, we could just factor it out to the front. Or you can distribute it with it, give you the same answer either way. Okay. So with this one, I'll go ahead and distribute the 3 with it, just to mix it up a little bit. Okay. So that gives us the integral from pi over 3 to pi over 2 of 3 times cosecant cotangent, or cotangent cosecant, plus 3 times cosecant cosecant. So cosecant times cosecant is cosecant squared. Okay, so now we take the integral of both terms. So we take the integral, or you can keep them together because they're both going from pi over 3 to pi over 2, or you can do them separately. It's completely up to you. Sometimes I'll keep them together, sometimes I'll separate them. Just depends on how you feel for that particular problem. Okay, so if we get that 3, again, we can factor that out to the front. We have the integral of cosecant of x times cotangent of x with respect to x, plus 3 times the integral from pi over 3 to pi over 2 of cosecant squared of x with respect to x. Okay, so the next step would give us 3 times the integral of cosecant cotangent is negative cosecant. That's negative cosecant of x. And that's from x equals pi over 3 to pi over 2. Plus, go ahead and bring that 3 out to the front. And we know that the integral of cosecant squared is negative cotangent. So that integral just becomes negative cotangent of x from pi over 3 to pi over 2. Okay, so now we just go ahead and apply the fundamental theorem to both terms. Okay, so that gives us 3 times, and we plug in our upper limit. You could have factored out the negative if you want to, but I'll go ahead and leave it in. That's negative cosecant pi over 2 minus, plug in our lower bound, negative cosecant pi over 3 plus 3. We do the same thing here, apply the fundamental theorem, times negative cotangent of pi over 2 minus negative cotangent of pi over 3. Oops. There we go. Okay, so that gives us 3 times. We have negative cosecant of pi over 2. Well, cosecant of pi over 2 is positive 1, and that will make that negative 1. So you have negative 1. This minus negative turns this plus, and cosecant of pi over 3 is 2 square root of 3 over 3. That's for this one, and that's for this one. Actually, didn't even need this extra bracket. It's small enough to where just use the parentheses. Okay, so plus 3 times cotangent of pi over 2 is 0. You have minus negative cotangent of pi over 3 is square root of 3 over 3. So positive square root of 3 over 3. And that one goes here, and this one goes here. There we go. Okay, so we distribute the 3. We get negative 3. And the 3's would cancel out here, so that's plus 2 square root of 3. And if we distribute this 3, we get plus 0, which we don't have to worry about putting down. I'll put it down anyway. And if we distribute the 3 here, the 3's would cancel out, so that's just plus square root of 3. So our final answer would be negative 3 plus 3 square root of 3. Make that 3 a little neater. All right, any questions on that one? All right. So let's say, for example, if we are given that the integral from 1 to 2x squared of t divided by t minus 7 with respect to t. And we want to find the derivative of that integral. Okay, now with this one, we don't have a real number for lower and upper limit. We actually have a function for our upper limit. So that one, we just have to remember that the integral from a to some function u of x of some function with respect to t is equal to your integral f of x. Okay. Now, if we had just a t here, or just a x here, then that would just be f of x. Or the integral of f of t is just equal to f of x. Okay, so what if we let our u of x, or u, equal 2x squared? Which means our derivative of u with respect to x, or you could put u prime of x, is equal to 4x. Okay. Now, we already know that I'll just rewrite that. instead of pointing up and down, is equal to the integral from a to some function u of x of f of t with respect to t. Now, if you remember part 2, put this up just for a second. On the very first page, we can see that when you have an upper limit that's a function, we're going to apply the chain rule. And this is one of those cases. But since we're trying to find the derivative, remember that's just going to equal your f of x, where your f of x is just your f of t, where it's t over t minus 7. So that's the integral from a to u of x of your t divided by t minus 7 with respect to t. Okay. With this one, you're going to take your u of x, and I'm just using a blanket u of x instead of actually plugging it in. Because this way you can kind of use this process no matter what your u of x is. We're going to replace every t with u of x. Okay, so this integral would just be u of x divided by u of x minus 7 times the derivative of your u of x. Now this is just your du dx and another notation. Okay, so now that u of x could just become 2x squared divided by 2x squared minus 7. Times your derivative of u of x, or your du dx, which is 4x. I'll just put times 4x. Okay, so if we go ahead and just combine these two, that would give us 8x to the third power divided by 2x squared minus 7. And we'll do another example like this one. All right. So let's say, for example, if we are given that uppercase f of x is equal to the integral from 3 to sine of x of t squared plus 8 with respect to t, we want to find our f prime of x. So again, we know that we're going to use the integral from a to some function u of x of f of t with respect to t is equal to f of x. Okay, so in this case, our u, or u of x, is equal to sine of x. And our derivative of u with respect to x is the derivative of sine is cosine. Okay, so again, I'm just gonna, I don't know why, but I like to write it down in steps. So you don't have to rewrite this if you don't want to, but I'm just gonna rewrite it from 3 to sine of x of f of t with respect to t is equal to your f of x, or uppercase f of x. Or f prime of x is equal to the integral of that is just plugging in your u of x. So again, I'd rather keep it kind of general so you can use it over and over. So I'll just, instead of that, I'll put u of x. So it can travel down and hopefully make more sense. Okay. So that's just going to equal, instead of t squared, we're going to replace every t with u of x. So that's u of x squared plus 8 times the derivative of u with respect to x. So all we did was replace every t with our u of x. And again, if you wanted to, you could have gone right ahead and just made it sine squared of x, but I just figured I'd keep it generalized. Okay, so this is equal to, since u of x is sine of x, that's sine of x squared plus 8 times your du dx is cosine of x. So you could leave it like that, or you can distribute the cosine, where you get sine squared of x times cosine of x plus 8 times cosine of x. They should take either form. I don't see them being too picky about one or the other. All right, any questions on that one? All right. Okay, let me put these together now before I lose them. There we go. Okay, anyone still writing? All right. Okay, so now we're going to go ahead and start on section 5.4, which is integration and the net change theorem. Okay, so first we're going to look at net displacement. And that's just the distance from where an object, I guess you could say the measure from where an object starts to where it ends in a straight line. So the measure in a straight line from where an object starts to where it stops. Okay, so that gives us the formula. We know that f of b minus f of a is equal to the integral from a to b of your velocity function with respect to x. Okay, so we know that the velocity function is just the first derivative. So if we take the integral of the first derivative, that leaves us with just our original function. So if we take that original function, plug in our upper and lower limits using the fundamental theorem, this is the formula we have. Or you can add f of a to both sides. And you have f of b is equal to f of a plus the integral from a to b of your velocity function with respect to x. And leave a little note here that f of x equals your position function and your v of x is just another notation for your first derivative, which is your velocity function. They said it's usually the notation for the velocity function. Every once in a while, I don't know if it's just bad programming or the computer actually trying to see if you understand it, they'll use v of x as just your position function, and they'll just say the function v of x. Okay? So if they say v of x as just the function, then they're just using v here, which isn't math illegal. It's just not really something that's done a lot. But normally they'll say v of x is your velocity function. But if they don't say velocity function, then it's quite possible that your v of x could be the position function, and they just incorrectly use the v for the instead of the f of x. So. Okay, so what if we wanted to find the net displacement? We would just do what we did up here and integrate the velocity function. Excuse me. Okay. So remember, just to point out, there's a reason I use the measure instead of the distance, because there's a difference between distance and displacement. And sometimes a visual helps. Okay, so let's say if you start right here and you stop right here. Okay, so if you go along this path all the way, that's your distance. That's the distance you traveled. But somebody moved my index card. If we just draw a straight line from where we started to where we stopped, that measures your displacement. And I'll just draw a little line up here. So that's why I hesitate. I almost said the distance from where you start to where you stop, but I had to remember that that wouldn't be completely accurate. I want to use distance to describe displacement, knowing that distance is something altogether different. Well, not altogether different, just different. All right. So let's say, for example, what if it's given that v of t equals negative 2t squared minus 3t minus 3 represents the rate at which air is escaping from a balloon. Okay, so you want to give the equation of the volume of the air in the balloon denoted by V after 6 minutes. Okay, so with this one, that V of t, they don't tell you that it's the velocity function, but you can tell just by the fact that it represents the rate. If it represents a rate of change, then you know that's your first derivative or your velocity function. So they may not come out and tell you, hey, this is the velocity function, but some wording will let you know. Like I said, if it says anything about this function represents a rate of change or the miles per hour or something like that, any rate of change, you know it's your velocity. But if it just says outright v of t represents a function, then it's just a plain ordinary function. Okay, so we know here just from what's given to us, that V is the volume of the air in the balloon. Okay. So we're looking for the volume after 6 minutes. So we know that after 6 minutes, we know our interval is from t equals 0 minutes to t equals 6 minutes. Or you can just say from 0 to 6. Okay. So does that make sense so far? Okay. Okay. So if we remember, you know that V of B minus V of A is equal to the integral from A to B of V of T with respect to T. And I just change this from F of B and F of A to V of B, V of A, just to match our velocity. Okay, so we know that our interval is from A to B. So A equals 0, B is equal to 6. So we know that V of 6 minus V of 0 is equal to the integral from 0 to 6 of our velocity function, which is -2 t squared minus 3t minus 3 with respect to t. So this would tell us our volume after 6 minutes. So we just add our volume at the beginning, add that to the other side. So our volume after 6 minutes is just equal to our initial volume plus the integral from 0 to 6 of -2 t squared minus 3t minus 3 with respect to t. So all they wanted to know was the equation. They did not want us to solve it. So we're going to leave it right there. So if they ask for just the equation, this is all they're looking for, is just the equation. All right, so any questions on that one? All right. So let's say, for example, if f of t, which equals -2t squared plus 5t minus 3, represents the rate at which a population is changing in thousands of people per year. Then find the equation that gives the size of the population after 5 years. Okay, so this is one of the tricky ones I was talking about. We know that it represents a rate of change. So we know it's a velocity function, but they used f of t. Okay, so you don't want to get too attached to your f of t only being the function or v of t only being the velocity function. Because sometimes they'll use f of t as your velocity function instead of your position function. So you want to look out for those little keywords that doesn't match the variable that you're used to. And I only point this out because I used to get so confused by that. I used to jump in and they'd have f of t as the velocity function. Then the next question, they'd have f of t as the position function, and I'd just be completely confused. So that's why I'm pointing that out. So hopefully you don't suffer the same confusion I did as a student. Okay, so we know that after 5 years, the interval is from t equals 0 to t equals 5. Okay, so since this is your velocity function, we know that f of b minus f of a is equal to the integral from a to b of your velocity function with respect to t. Okay, so if we add f of a to both sides, we have f of b is equal to f of a plus the integral from a to b of f of t with respect to t. And if we plug in our a and b and our f of t, we just end up with f of 5 is equal to f of 0 plus the integral from 0 to 5 of your velocity function, negative 2 t squared plus 5t minus 3 with respect to t. All right. Any questions on that one? All righty. So let's say, for example, if the velocity of a particle that is in motion is v of t is equal to t minus 15 meters per second. We want to know what is the net displacement of the particle from t equals 5 seconds to t equals 9 seconds. So we know that our net displacement we know that is just the integral from a to b. Our velocity function with respect to t is equal to v of b, let's say f of b minus f of a. Okay, so really we're just going to start with this, and we'll eventually end up here anyway. So you have the integral. Now you would use this side if you had the position function. Now if they gave you the position of the particle is given by this function, then you just plug in your 9 minus 5, and then you'd be all set. Well, plug in 9, and then you subtract when you plug in 5. Then that'll give you just your displacement if you're given the position function. But since we're given the velocity function, we have to use this, which is the integral of the derivative, which gives us our position function. Okay, so we know the integral from a to b of our velocity function with respect to t is equal to, you see it's from 5 seconds to 9 seconds, so that's our a and b. That's the integral from 5 seconds to 9 seconds of your velocity function, which is t minus 15 with respect to t. So if we integrate each term, again, we can do them together. We have the integral of t, or t to the first power, is t squared divided by 2, minus the integral of 15 is just 15t. And that's from t equals 5 to t equals 9. So from there, we apply the fundamental theorem of calculus. Let's clean that up a little bit. So we plug in our upper limit, move that over to make sure we have enough room. So we have 9 squared divided by 2. Minus 15 times 9. Minus, now we plug in our lower limit, so that gives us 5 squared divided by 2. minus 15 times 5. Okay, so 9 squared divided by 2, that's just 81 divided by 2. Minus 15 times 9, which is minus 135. Minus 25 divided by 2. Minus 15 times 5, which is 75. Okay, so there's 135. We could rewrite that as 270 divided by 2. And this 75, we could rewrite that as 150 divided by 2. Okay, so we have 81 divided by 2 minus 270 divided by 2, which is negative 189 divided by 2, minus 25 divided by 2 minus 150 divided by 2 gives us negative 125 divided by 2. Which gives us 64 divided by 2, which is negative 32. Well, negative 64 divided by 2, which is negative 32. All right, any questions on that one? Yes.
For the net displacement equation, back in your example of the distance between net displacement and distance, you showed distance as being like the length along the curve, and
Yes.
displacement as being the distance between the 2 points, if you view it that way.
Yes.
But the equation makes it look like f of b minus f of a, that's just the difference in the outputs of the functions, like the distance in y instead of the distance between the 2 points, or
Yeah. That's exactly what it is.
Okay.
Yep, so just the integral of your velocity function. All that does is give you your, because if you have some function from here to here, and let's say this is from A to B, let's move this over just a little bit. And that means that this is your, should have moved it over a little bit more. F of A, and this is your F of B.
Okay, so
yeah. So all we're doing is measuring the distance between F of A and F of B, just saying that we can just get that same distance or same displacement just using the integral, but only when we're given the velocity function.
Right.
Okay, good catch. All right, any other questions on that one? All right. So what if your velocity changes on a certain interval? So what if we know that the velocity function corresponds to the motion of a particle? Okay, so if measured in meters per second, what is the net displacement of the particle for the first 5 seconds. We know that our velocity function is equal to negative 3t plus 2, but only when your time is between 0 and 2 seconds. And make that less than or equal to a little bit clearer. And it's 2t minus 8, but only when your time is between, not equal to 2 seconds, but everything after 2 seconds, all the way up to 5 seconds. So this would be useful, let's say, if you're observing the velocity of a bee flying for whatever reason. Maybe you're getting research grants to do that. And from the first 2 seconds, the bee is flying and you jot down all of the data and you come up with this velocity function. Let's say the wind picks up, and for the last 3 seconds, he's flying at that velocity, or picks up or blows against him, slows the bee down, who knows. But let's say, so it would help with something like that. Or you can apply it tons of other areas. So the velocity is changing between 0 and 5 seconds. So with this one, all you have to do is remember that we can take our integral from a to b of f of x with respect to x, and we can split it up as the integral from a to some value c of f of x with respect to x, plus the integral from c to b of f of x with respect to x. Okay, which is perfect for this one. Because that means we can take our integral from 0 to 5 seconds of our velocity function with respect to t, and we can make that equal the integral from 0 to 2 seconds of our velocity function with respect to t, plus the integral from 2 to 5 seconds of our velocity function with respect to t. Now, I left it as v of t purposely because the velocity function you use all depends on the interval. So from 0 to 2 seconds, this is our velocity function. And let me move this over a little bit further. So we have the integral from 0 to 2 seconds of negative 3t plus 2 with respect to t. Plus, now from 2 to 5 seconds, this is our velocity function. So we have 2t minus 8 with respect to t. Okay? So whenever you're given a piecewise function of a piecewise velocity function, then you already know 9 times out of 10 you're going to have to split it up like this. So if they gave you 3, let's say from 0 to 7, and the last one was a different function, then the first one would be from 0 to 2, second would be from 2 to 5, third one would be from 5 to 7. So you can split it up to match as many velocity functions as you have. Okay, so now we have to take the integral of each of these terms and the integral of each of these terms. So if we factor out that -3, we have the integral of t, actually just the -3 for the first term. The integral of t is t squared over 2 plus the integral of 2, which is 2t. And sometimes you'll see the notation from t equals 0 to 2. So let's make that 0 a little bit neater. Plus the integral of 2t. Well, if we factor out the 2, the integral of t is once again t squared over 2 minus the integral of 8, which is 8t. And that's from t equals 2 to t equals 5. Okay. So here we can apply the fundamental theorem to both terms. Okay, so that gives us -3 times 1/2. We can just combine those and make it -3 over 2. Okay, so if we plug in our upper limit, that's -3 over 2 times 2 squared plus 2 times 2 minus, now we plug in our lower limit. I'm going to try and write this as small as possible to fit everything on there. So that's -3 over 2 times 0 squared plus 2 times 0. Had to remember to not give as much space. Okay, so that was for this one. Minus, now we apply the fundamental theorem to these two terms. Plug in our upper limit. So these 2's cancel each other out. So that just leaves t squared for that one. So that gives us 5 squared minus 8 times 5 minus, plug in our lower limit, 2 squared minus 8 times 2. I had like 1/8 of an inch to spare. Okay, so we know that this term here is just 0 plus 0, so that completely disappears. Okay, so we have 2 squared, which is 4 times -3, which is -12 divided by 2, gives us -6. Clean that up a little bit. There we go. And this one is just 0, so, oh, actually almost missed the 4 here. Plus 4. And that 0 just disappears. Why am I randomly throwing in minus signs so much? Goodness. Okay. Plus should have been the minus in there, not between those two integrals. So make sure you put the plus between those two. Okay, so we have 5 squared, which is 25, minus 8 times 5, which is 40. So that gives us minus 15. Minus, we have 4 minus 16, which gives us negative 12. But if we distribute that negative, that makes it plus 12. Okay, so that gives us negative 2 plus negative 3, which is equal to negative 5. Oops, straighten that up. All right, so any questions on that one? All right. Go. So let's say if Jack and Roy are ice skating. So we want to know whoever skates the farthest after 8 seconds in a straight line wins. There we go. Okay. So we know that Jack skates at a velocity of f of t is equal to 11 plus t. Let's separate those a little bit better than that. Feet per second. And we know that Roy skates at a rate of, I'll put that below it, g of t is equal to 17 minus sine of pi over 3t feet per second. So who wins the race? Oops, separate that a little bit. Oh, I'm so tired of rain. I think it's supposed to rain the next 2 days. Excuse me. Since we know that, let's say if we wanted to find out Jack's displacement. Okay. Now with this one, we know it's after 8 seconds, so it's from the interval from 0 to 8 of his velocity function, which is 11 plus t with respect to t. So if we take the integral of each, move that over a little bit, of each term, the integral of 11 is 11t. Plus the integral of t is t squared over 2. And we know that's from t equals 0 to t equals 8. So if we apply the fundamental theorem here, we plug in our upper limit. That's 11 times 8 plus 8 squared divided by 2 minus, now we plug in our lower limit, 11 times 0 plus 0 squared over 2. And if you wanted to, whenever you see t is equal to 0, if every term just turns to 0, I would just put minus 0 or leave it blank. But I just do this for visual purposes. Okay, so we have 11 times 8, which is 88, plus 8 squared is 64, divided by 2 is 32. So Jack had a displacement of 120 feet after 8 seconds. Okay, so let's go ahead and just separate that. I'm going to leave this side kind of open for a reason. That's because for Roy, we know that from 0 to 8 seconds, his velocity function is 17 minus sine of pi over 3 t with respect to t. Move that up a little bit. There we go. So if we take the integral of 17, and that gives us 17t. Okay, minus, and the reason I had this separate area here is because for this problem, to solve the integral of sine of pi over 3 times t, we'd have to use what we're going to cover in 5.4, which is u substitution. So this is kind of a sneak preview of 5.4. So we're going to take the integral of sine of pi over 3. So let's make that a little clearer. Times t with respect to t. Yes. Oh, that's, yep, 5.5. We start at 5. Okay, yep, 5.5. Thank you. Yep, 5.5. I think because we started 5.3, I forgot we switched over to 5.4. Okay, so normally if you had just the integral of sine of t by itself, it would just be basic cosine of t, or negative cosine. But because we have that value in there, we can't just multiply it by g of x or g prime of x like we could with derivatives. Okay, so with this one, we're going to let u equal pi over 3 times t. Which means our derivative of u is equal to, the derivative of t is just 1, so we have pi over 3 dt. And move this arrow over just a little bit. Okay, so we want to get our dt by itself, so we multiply both sides by the reciprocal of pi over 3, just 3 over pi. And multiply this side by 3 over pi. Where these two cancel each other out, because if you multiply them, it just equals 1. So we know that 3 over pi du is equal to dt. Okay. So we're going to take this u and this dt, we're going to plug it into our original integral. Okay, so sine of pi over 3t, we can just make that the integral of sine of u. And that dt, we're going to replace that with 3 over pi du. So that 3 over pi, we're just going to factor that out to the front. So we have the integral of sine of u du. Okay, so now our independent variables match. Okay, so we didn't have, even though this was still a function of t, that pi over 3 made it to where you can't just have the integral of sine of t, because that pi over 3 was there. So we had to kind of convert it to another variable to where it's just the integral of sine of some variable with respect to that same variable. Nothing else can be inside of there. So that's why we replace it with a u. Okay, so we know that the integral of sine is negative cosine. So that's 3 over pi times negative cosine of u plus c. Okay, so if we factor out that negative, that just gives us negative 3 over pi times cosine, and replace that u with pi over 3t. Make that a little bit bigger. Pi over 3t plus c. Okay, so now we have the integral of 17 is 17t minus the integral of sine of pi over 3t is negative. We can go ahead and, since it's minus negative, and make that plus 3 over pi times cosine of pi over 3 times t. And that's from t equals 0 to t equals 8. Excuse me. Okay, so now we can go ahead and use the fundamental theorem. So we plug in our upper limit, and I'll lower this a little bit to make sure it clears that little box here on the side. So if we plug in our upper limit, we get 17 times 8 plus 3 over pi times cosine of pi over 3 times 8 minus, now we plug in our lower limit, we have 17 times 0 plus 3 over pi times cosine of pi over 3 times 0. And let me use brackets so it's not a million parentheses. At least for the outer ones. There we go. So when you're plugging in the zeros, be really careful. You know that 17 times 0 is 0, so that would disappear. And pi over 3 times 0 is 0, but that gives us cosine of 0, which is 1. So not plugging in every 0 eventually all becomes 0. Sometimes plugging in 0, like in this case, can give you an actual value. Okay, so we have 17 times 8, which is 136, plus 3 over pi times cosine of 8 pi over 3 minus 0. Oh, let me see. Yep. So that's plus, and remember, that's just 3 over pi times 1, which is why'd I put plus? Which is minus 3 over pi. So plug that into your calculator, because I didn't even try to figure out what cosine of 8 pi over 3 is. I just plugged it all into the calculator. You get 134.6 feet. Okay. So in this case, Roy would win. Okay. So every once in a while, they will kind of jump ahead a little bit and give you a problem with a method that you haven't seen yet. And this would just be one of those examples of not seeing this until the next section. Why I don't know if that was a programming error or what, but sometimes they do it. All right. Any questions on that one? All right. So let's say for the next example, let's say that a car accelerates at a rate of, say, a of t is equal to 1 over 10 t squared minus t meters per second. Determine how much the velocity increases between 5 and 15 seconds after first accelerating. Make that L a little neater. There we go. Okay, so this is another one that can be really tricky if you're not being careful. And that's because you want to remember that f of t, that's your position function, your v of t, or your first derivative of your position function, is your velocity function. And a of t, which is the first derivative of your velocity function, or the second derivative of your position function, that's your acceleration function. Okay, so write that as its own little box, and then I'll write the rest as a separate box under it. Okay, so if we took the integral from a to b of your acceleration function, that's like the integral of the second derivative. So the integral of that second derivative would cancel out with one of those derivatives. So that would just be the first derivative. So that would equal the first derivative, which is your velocity function. So that would be v of b minus v of a. Okay, so with this one, even though we're taking the integral of the acceleration function, in this case, that's going to give us the velocity function's displacement. Now, that's why the velocity function gives us the position function's displacement, because the integral of that derivative, or one of those derivatives, will cancel out. Okay, so we know that we have the integral, and we're looking for between 5 and 15 seconds. So the integral from 5 to 15 of our acceleration function, 1 over 10 t squared minus t, with respect to t, and we're going to integrate both of those terms. So that gives us 1 over 10 times the integral of t squared, t to the third power over 3, minus the integral of t to the first power is t to the power of 1 plus 1 divided by 1 plus 1. And that's from t equals 5 to 15 seconds. Okay, now this is our velocity function. So if we're looking for the change in velocity, once we apply the fundamental theorem, that'll give us the change at 15 seconds minus the change at 5 seconds. Okay, so if we plug in t is equal to 15, move that equal sign over to make sure we have enough room. So this just becomes 1 over 30, so we can go ahead and combine it, or you can leave it like that. So we have 1 over 30 times 15 to the third power minus 15 squared over 2 minus, now we plug in our lower bound, so that's 1 over 30 times 5 to the third power minus 5 squared over 2 So plug in 15 to the third power into your calculator. That'll give you 3,375 divided by 30. Minus 15 squared over 2 is 225 divided by 2. Minus 5 to the third power, which is 125 over 30. Minus 5 squared over 2, which is just 25 over 2. Oops. Okay, so if we multiply this one by 15 over 15, then simplify, we'd end up with negative 25 over 6. And if we multiply this one by 15 over 15 and simplify, we'd end up with negative 75 over 6. But if we distribute that, it becomes plus 75 over 6. Which gives us positive 50 over 6. But if we want a decimal approximation, that's just approximately 8.3 meters per second. All right, any questions on that one? Okay, so sometimes they may even say, if they give you the acceleration function, if they ask you to find the net displacement, then you actually have to integrate this twice. You'd have to integrate it till you find your velocity function. Then you have to integrate this again to find your position function. So like I said, it varies question per question. And they update new questions every few months. So I try to get as many examples of the difficult ones as I can. But like I said, they change it. They may have one question up there today and a different one in the rotation next week. So, all right. Any questions on that one? All right. Okay. So yesterday we kind of peeked into integrating even and odd functions. So we're going to go a little bit further into that one. Okay. So again, we know that if a function is even, we know that the integral from negative a to a of f of x with respect to x is equal to 2 times the integral from 0 to a of f of x with respect to x. Just kind of a quick little refresher. So visually, all that means is that if we have an xy axis and we have an even function, which means on either side of your y-axis, it looks like a mirror image. Okay, so let's say if we have, try to make that as visually accurate as possible. And move that over just a little bit, just to make that actually look symmetric. There we go. Okay, so let's say you're looking for the integral from negative a to some value a. Say from negative 3 to 3 or negative 5 to 5. So since these two sides are symmetric, all you'd really have to do is find the integral of the side from 0 to a, and then just multiply by 2, because if you flip it across here, this side and this side will be the same area. And if a function is odd, then we know that the integral from negative a to a of f of x with respect to x would equal 0. Okay, so all that means visually is that if you have some odd function, okay, so let's say you have some odd function, kind of look like that. Pretty similar to like x to the third, the function of x to the third power. And we're looking for the integral from negative a to a. Okay, so we know if we have this area here, which is above the x-axis, so we'll call that area number 1. And this area here below the x-axis, we'll call that area number 2. Then the integral is just the net area. So we know that the integral from negative a to a of f of x with respect to x is going to equal area number 1 minus area number 2. And since it's symmetric across the origin, those two areas are equal. So if you subtract them, just 0. All right. So let's say, for example, we want to know, can the integral from negative some value p to positive some value p of negative 3x to the 8th power minus x squared plus 5 with respect to x be rewritten as an odd or even integral? Okay, so in order to find out whether or not it can be rewritten as an odd or an even integral, we have to find out if this is odd or even. So first thing we have to do here is find out if your f of x is equal to negative 3x to the 8th power minus x squared plus 5 is odd or even. Okay, so the test to find out if it's even, I'll just put it as a little note here. I don't know if you remember it, but if you don't, this way it's a bit of a refresher. So the even test, we're just going to replace x with negative x. Oh, a little bit too high there. And if you do that, you should end up at the very same function. So if you replace x with negative x, you should end up right back at f of x. And the odd function test, you're going to replace x with negative x. And you should get the negative of your original function. So you replace x with negative x, it should equal the negative of your original function. Okay, so that's just in case. I know you've gone over this in pre-calc and intermediate algebra and all those, but just in case you forgot it. Okay, so now let's just replace x with negative x. So f of negative x is going to equal negative 3 times negative x to the 8th power. So negative 3 times negative x to the 8th power minus negative x squared plus 5. Okay, well, we know that negative x to the 8th power, that's just negative x times negative x times negative x times negative x, so on and so on 8 times. Multiply it to itself 8 times. Well, if it's an even exponent for that negative factor, then all those negatives cancel each other out. So that's just x to the 8th power. Same thing with negative x squared. Negative times negative would be positive, so that's just positive x squared. So that means f of negative x is equal to negative 3, and this negative x to the 8th power just becomes x to the 8th power. Minus, and this negative x, and that quantity squared just becomes x squared. And that plus 5 just stays as plus 5. Okay. So replacing x with negative x just gives us our original function. So it's equal to f of x. Okay, so since f of negative x is equal to f of x, we know it's an even function. So if it's an even function, that means that the integral from negative p to positive p of negative 3x to the 8th power minus x squared plus 5 with respect to x, we can rewrite that as an even integral of 2 times the integral from 0 to p of negative 3x to the 8th power minus x squared plus 5 with respect to x. All right, so any questions on that one? Okay, so again, hopefully the positive and negative functions test look familiar if it hasn't been that long ago. But again, if you forgot, it's perfectly normal if you don't use it a lot. All right. All right. So let's say we want to know, can the integral from negative k to k of negative 5x to the 9th power minus 2x to the 3rd power with respect to x be rewritten as an odd or even integral. Okay, so just like before we can rewrite it, we have to find out whether this is an odd or even function. And we know that if it's an odd function, then if we replace x with negative x, we get the negative of our original function. And if it's an even function, we replace x with negative x. We just get our original function. So either way it goes, we're going to have to replace x with negative x. Oh, make sure. Yep. So we're going to replace x with negative x. So that means that f of negative x is going to equal negative 5 times negative x to the 9th power. Minus 2 times negative x to the 3rd power. Okay, so whenever your negative x is raised to an odd exponent, it's going to come back as negative x to the, well, in this case, negative x to the 3rd power. So let's look at negative x to the 3rd power. Well, that's just negative x times negative x times negative x. Okay, so if you multiply these two, negative x times negative x, the negative times negative is positive. So you get this positive times this last negative one that's still here. So that positive times negative will give you a negative. And it'll work out that way for every odd exponent for negative x. So that's just negative x to the 3rd power. Or you can say negative 1 times x to the 3rd power. And same thing for negative x to the 9th power. Because it's raised to an odd exponent, that's just going to be negative 1 times x to the 9th power. Okay. So our f of negative x is equal to negative 5 times negative x to the 9th power. You can say negative or negative 1, whichever one, times x to the 9th power, minus 2, and that negative x, that whole quantity raised to the 3rd power, is just negative x to the 3rd power. Okay, now for these two terms, you're going to actually factor out one of those negative ones. So that gives you f of negative x is equal to, if we factor out those two negatives, that's just -1, or you can just leave it as a negative. So you have -5 times x to the 9th power minus 2 times x to the 3rd power. So this part here, that's just your original f of x. So this is just your f of x. But it's the f of x, now it's multiplied by -1. That's equal to negative f of x. So we see that f of negative x is equal to negative f of x, which means it's an odd function. I'll write out actual odd function. So since it is an odd function, we know that if we rewrite it, the integral from negative k to k of -5x to the 9th power minus 2x to the 3rd power with respect to x is actually just going to equal 0. All right, any questions on that one? All right. So let's say if we want to know, can the integral from -n to n of -4 times cosine of x with respect to x be rewritten as an odd or even integral? Uh-oh. Okay, so once you start getting into the trig function questions, all you have to do is remember that cosine and secant are the only even trig functions. The rest are odd. Only even trig functions. We'll make that even a little clearer. We'll make that one extra little note there. So that means cosine of negative x is equal to cosine of x. And secant of negative x is equal to secant of x. It's just their trig version of f of negative x is equal to f of x for both of those. So again, just a little side note in case you forgot that part about the trig function. Okay, so to kind of break it down, we know that our f of x is equal to negative 4 times cosine of x. And we know that f of negative x would just be negative 4 times cosine of negative x. Okay. We know that cosine of negative x, that's equal to cosine of x, because cosine is an even function. So f of negative x is still equal to negative 4 times cosine of x, which is your original function. And again, once you saw it was cosine, you could have just automatically said it's even and went right to the last part, but this is just kind of breaking it down step by step. So since f of negative x is equal to f of x, but we already knew it from the beginning note, we know that this is even. Okay. So again, these steps were kind of unnecessary, but figured I'd show you anyway. So if it's an even function, then we know that we can rewrite the integral from negative n to n of negative 4 times cosine of x with respect to x. We can rewrite that as 2 times the integral from 0 to n of negative 4 times cosine of x with respect to x. Okay, so even functions, you can just rewrite like this. Odd functions, we're going to equal 0. All right, so any questions on that one? All right. So let's say we want to know, can the integral from negative n to n of negative 5 times sine of x dx be rewritten as an odd or even function? Okay. So this one you want to remember that sine of x is an even function. I mean, not even, odd function. Thinking of cosine is an odd function. which means that sine of negative x is equal to sine of x, negative, so times -1. Give that a little more room. There we go. Okay. So again, really you can kind of skip just the fact that we already know it's an odd function. This part right here, you can really skip that because all this does is prove that it's odd, but we already know it's odd, so we can skip all of that. So because we know it's odd, we know that the integral from -n to n of -5 times sine of x dx is going to equal 0. Because we know that's for an odd function. So once you know if it's even or odd, it's a pretty quick solve. Like I said before, that for cosine, it's kind of showed each individual step. All right. So any questions on that one? All right. So now we can put these together. There we go. There. Okay, so now we can get started on section 5.5, which is U substitution. We kind of had a sneak peek at it already. So what if we let u equal some function of x? Then if we put it in differential form, if we find the derivative of u, that's equal to g prime of x dx, where we know that g prime of x, or the derivative of our original function, is continuous. Over some interval and sometimes they'll just say the interval I, but just I is equal a to b. Sometimes they'll just use I by itself. That's all that means. Okay. So what if we also let f of x be continuous over the range of g of x? And if we let our uppercase f of x represent our antiderivative. Of f of x, or lowercase f of x. Well, if that's the case, then we know that the integral of f prime of g of x times g prime of x respect to x is equal to the antiderivative of g of x plus c. Okay, but a simpler way to write is, remember that g of x, we let that equal some variable u, and g prime of x dx, that's equal to our du. So this g prime of x, we can also change it to u. So if we wanted to, we could rewrite it as the integral of f prime of u du is equal to the antiderivative of u plus c. Excuse me. Okay, so the definition looks a lot worse than the actual application. So hopefully once you see it a few times, it kind of makes sense. But in most cases, the definition looks worse than actually using it. Right. So let's say, for example, if we wanted to integrate, let's say, the integral of 6x times negative x squared plus 5 to the 7th power with respect to x. Okay. Now for this one, we can't just distribute the x because it's negative x squared plus 5 to the 7th power. So we'd have to expand that all the way. So negative x squared plus 5 times negative x squared plus 5 times negative x squared plus 5. We'd have to do that 7 times, then distribute and combine like terms and all of that, and then distribute to x to each of those terms. So instead of going through all that, we're just going to use the chain rule. So that's 6, that constant, I usually factor out my constants. So we have 6 times the integral. And I'm just going to switch these up. You don't have to. But I do it just to kind of match things up. So the negative x squared plus 5 to the 7th power times x, I just switch those up. Doesn't change any values. Okay. So for this problem, I'll just mark this over on the side. We're going to let u equal negative x squared plus 5. Okay, so we're going to need that. So let's circle that so we can come back to it. Which means if we found the derivative of u, that's equal to the derivative of negative x squared. If we bring down the 2, that's negative 2 times x to the power of 2 minus 1. So that's just negative 2x. Plus the derivative of 5 is 0, so that disappears. So it's negative 2x dx. So if we divide both sides by negative 2, let me do that as a separate step. So negative, actually, instead of dividing it by negative 2, I'll make it -1/2 times du is equal to x dx. Or you can multiply both sides by -1/2. Okay, so I'm just going to rewrite this down here. So if we have our 6 times the integral of -x squared plus 5 to the 7th power times x dx, you know that this part right here, the -x squared plus 5 to the 7th power, we can replace that -x squared plus 5 with u. So this just becomes u to the 7th power. And this x dx, we can just replace that with -1/2 du. So that means we can rewrite this as 6 times the integral of u to the 7th power times -1/2 du. And that -1/2, we can factor that right on out to the front. So that's 6 times -1/2 times the integral of u to the 7th power du. Or you could have simplified it before that, but we'll simplify it here and just make that -3 times the integral of u to the 7th power du. Now, if you remember, if we have the integral of x to the 7th power dx, then that's just x to the power of 7 plus 1 over 7 plus 1 plus c. Same thing here. As long as you have it in the same form where you have u and du, then you can do the same thing here. So you have to -3 times the integral of u to the 7th power is just u to the power of 7 plus 1 over 7 plus 1 plus c. And that gives us, if you factor out that 1 over 8, that gives us -3 over 8 times u to the 8th power plus c. Okay. So once it's all integrated and simplified, the only step left is to replace your u. And we had u is equal to -x squared plus 5. That's equal to -3 over 8 times -x squared plus 5 to the 8th power, because it's u to the 8th power, so we make that to the 8th power plus c. And that's our integral. All right, any questions on that one? All right. let's say if we wanted to find the integral of negative 2x squared times x to the third power plus 6 to the fourth power dx. Okay. So again, just for me, I always factor out any constants just to make this as simple as I can. So factor out that negative 2 times the integral of x squared times x to the third power plus 6 to the fourth power dx. Okay. So for this one, we're going to let u equal x to the third power plus 6, which we're going to need later, so we'll circle that to come back to it. Which means our derivative of u is equal to, well, the derivative of x to the third power, we bring down the 3 and subtract 1, so we have 3x squared, plus the derivative of a constant is 0, so that disappears. So that's 3x squared with respect to x. Okay. So if we divided both sides by 3 or multiplied both sides by 1/3, we have 1/3 du. Multiply this side by 1/3, the 3 would cancel out. That's equal to x squared dx. Or you can divide both sides by 3. Either way works. Okay, so if we rewrite this, and again, I'm just rewriting it for visual reasons. You don't have to do it. We're just going to switch up this x squared and put it next to the dx. So we're going to switch those two up. So you have x to the third power plus 6 to the fourth power times x squared dx. Okay, so now we know that we can rewrite this as u to the fourth power. And this x squared dx, we can rewrite that as 1/3 du. So that gives us negative 2 times the integral of u to the fourth power times 1/3 du. So if we get that 1/3 and move it out to the front, that's just negative 2 times 1/3 times the integral of u to the fourth power du. So if we had the integral of x to the fourth power dx, then that would just be x to the power of 4 plus 1 divided by 4 plus 1 plus c. With this one, same thing. Negative 2 times 1/3, we can just make that negative 2/3. And the integral of u to the fourth power is u to the fifth power over 5. times u to the 5th power over 5 plus c. So if we multiply our denominators, that gives us negative 2 over 15 times u to the 5th power plus c. So again, once we have it all simplified and integrated, the last step is just to replace the u. And in this case, u is equal to x to the 3rd power plus 6. So this just becomes negative 2 over 15, and instead of u to the 5th power, it's x to the 3rd power plus 6 to the 5th power plus c. All right, so any questions on that one? All right, so we'll go ahead and stop there. We'll finish this up tomorrow. So hopefully we'll finish 5.5 and 5.6 tomorrow. And let me check. I think 5.7 trig inverse. Yep. So we have 5.7 and 6.1 hopefully done by Thursday, but if not, at the latest Monday. Then after that, I'll be here, but we won't have any actual lectures. So if you want to come in and ask questions, you can. But that's all for today. Again, if you have questions today, feel free to hang back and ask. But if not, see you too. I'll see you tomorrow.
How was some like practice stuff for this class?
Hmm?
The final practice exams for this class?
Mhm.
Is this the calculator they get on the final? Because that's the one that was showing me on the website.
Honestly, I've never seen it, so I'm
Because it
not
said
sure.
This is the one that would show on the top.
Oh, okay.
Yeah.
Yeah, but
But
it
it's just
might
because
be.
like this one's like really basic. That's why. I
Yeah,
was
it might
confused.
be.
You
Yeah,
think so?
it might be.
Wow. Okay.
Yeah, I've never seen the calculator, but
Yeah.
it's possible that could be
It's
the
that
one.
digital
Yeah,
one.
so they'll always design questions to where
Like-
that calculator should
Okay,
be.
like they won't do like stuff like secant and like.
Oh no,
yeah.
if they
Okay.
do, it'll be just using the kind of
Like
the
unit circle,
basics.
like 1
Yeah.
0.
Yep, it'll just use the
Okay.
basics. So
Okay.
they might use like secant or something outside of the
Yeah,
unit
'cause
circle.
it's just 1 over. Yeah.
Yeah,
Yeah.
but
Okay. But
yeah.
like not like something crazy.
Oh yeah, they won't. Yeah, they give
Okay.
you just that basic calculator. They design the questions just to be to where those questions
You can do
can
them
be
without a
answered.
calculator, basically.
Yeah.
Okay, gotcha.
Yeah.
Thank you.
You're welcome. Hello.
How are you?
I'm good. How are you?
Good.